Oh man, I should have a stopwatch going. Video 1 of this series was 14 minutes long. Apologies for that. I like to keep them a little shorter when I can, but it is what it is. So next definition, let f be a function with domain D, and we're going to pick a point in the domain. I want to give you a series of 4 definitions, all of which are very similar, just a couple of differences that we want to highlight. So f has a local max of f of c at x equals c. That language is important. Local max of f of c at x equals c if, when you plug in c into f, that's greater than or equal to whatever else you plug in for any point that's near c. And we're going to see this visually in just a moment. All right? So f of c is greater than or equal to f of x for all x near c. F has an absolute max of f of c at x equals c if the same inequality holds, but this time not just for x near c, but for all x in the domain of f. This literally is the highest value you can possibly get when you plug points in the domain into your function f. Okay? And then similar definitions for min. Local min of f of c at x equals c if this time f of c is the small one, it's less than or equal to f of x for all x near c. And then f has an absolute min of f of c at x equals c if it's f of c is less than or equal to f of x for all x in the domain D. So like many things in mathematics, you need precise definitions, or at least as precise as one can. Actually, this language, x near c, you're allowed to be a little bit questioning what that means. I'll show you visually, but if you really want to find out what that means, I would highly encourage you to sign up, be a math major today, and then you can take Intro to Real Analysis, and you will know what x near c means in that class. But for now, we'll have to just get by with that language. Okay, so let me do a remark, and then I'll show you via picture. Pictures are how you learn things often when we're trying to understand. So absolute extrema can occur at endpoints of your interval, but local extrema cannot occur at endpoints. So let me draw a little picture for you. All right, and so let's switch colors. I'm feeling like that color today. So we'll do something like this right there. Okay. So here is my function, and now I'm going to, oops, I don't really like how steep that is, but whatever. All right, so I just want to point out the local and the absolute extrema to you. Local extrema for a continuous function are pretty easy. It's just the high points, the peaks of the mountain, so to speak, and the low points, the peaks of the valley. So this is a local maximum, local minimum. You know nothing local can happen at the endpoint, so you don't have to check those. That's easy enough. All right. Absolute extrema is just quite literally the highest point you can hit. So if you look across here, that one is higher, and this one is the lowest point. So f has an absolute max right here. Yes, it also has a local max right there. That's okay. You can have this both happening at the same point. F has a absolute minimum right here. So we would say that the minimum is the y value happening at the associated x value. All right, so that's absolute extrema. Now, we're going to tackle this question of how do you find local extrema. Extrema just means min or max. How do you find local extrema or absolute extrema? And we're going to start by learning how to find local extrema. And then towards the end of this chapter, we'll pick up a theorem that at least gives us some ideas on how to find absolute extrema as well. So we'll get to that, but I want to begin by finding local extrema. So just a couple of comments before we go on. One comment is that the word local sometimes can be replaced with the word relative, and it means the same thing. You might Google and do some reading, and you'll discover that someone will talk about a relative min or a relative max. That's the same as local min or max. The other comment is, the way that I've drawn this picture for this example, my function is continuous. So there's no holes or jumps or anything like that. You can draw other pictures of non-continuous functions where life gets a little bit interesting. I think I won't show you one, but it would be, if you would like to think about that, feel free to shoot me a message on Teams and you can draw a picture, or I'll draw one as well. Actually, I'll tell you what, I will pose a question, and if you want to think about it, you can, but if you don't want to, you don't have to. So here's the question that you can ask yourself. If I do something like this, and then I'm just going to have a hole here, and then I'm going to put this right there. So the question is, what's happening at that point? Is this particular x value, is this a local min? Is it a local max? Is it nothing? What is it? And you're welcome to just ignore that. If you want to think about it, go for it and shoot me a message on Teams if you get it. All right, so I'll end this video with an interesting result. This is known as Fermat's theorem. This is not Fermat's last theorem. If you don't know what Fermat's last theorem is, you should immediately pause this video and go Google and find out a little bit about his last theorem. Very famous result that kept mathematicians busy for centuries. It was only proven in the late 1900s. Really interesting result that you'll be able to understand the statement. I think the BBC has a documentary on Fermat's last theorem. It's very old, and you'll be appalled at the graphics. They're bad, but it's a really interesting video. I think it's on YouTube. You might check it out if you're bored. There's nothing better to do, right? Might as well watch some old math videos. What could be more fun? All right, so we are doing not Fermat's last theorem. We're going to look at Fermat's theorem. And Fermat was often is not credited as being one of the discoverers of calculus. But really, in some ways, he saw a lot of these ideas before Newton did. And what Fermat saw was that, look, if you have a local extrema at a particular x value, and, by the way, you know the derivative exists at that point, then you know something. And let's look up at our example. What do you notice about the tangent line at this local max? What's the slope of the tangent line? It is, and the slope of this tangent line is, and the slope of this tangent line is, they're all 0. And so Fermat says, look, as long as the derivative exists, then, and there's a local extrema there, then f prime of c, f prime at that point, has to be 0. So this is a really interesting proof. I'm so tempted to prove it, but I think this video series is going to be long enough without that. So I won't prove it. Man, open your book and look at the proof. It's really quite nice. I'll stop this video here. In the next one, we're going to look at what Fermat's theorem isn't saying. It's really important that we don't assume more than what it's actually telling us. So that's where we'll go.